We can hear you now.
Hey.
Sorry about the delay.
No, that's okay. Okay, I think I can begin, right?
I believe you can begin, yes.
Okay. Hello, my name is Kirill, and I want to talk about how we implement the separation logic by representing frame rule application as discharged queries. This work is done in the context of finite type system for Java, called Java, which we extended with separation logic. But the talk itself is not about liquid Java precisely, but about things that found not work. So there are many things, many tools which allow programmer to read about code with some kind of special logic, and some of them are powered by SMT solvers like Piper, Smallfoot, G-Star. And from a certain point of view, there are simplifications they look which might similar. And the code analysis which they perform needs some logical statements here. And these logical statements are transferred to first-order logic, is then fed to SMT solver, which provides feedback with errors and warnings. But logic statements are not created equal, and some of them are easily translated to first-order logic, some not so much. And special logic falls into not so much paper. If one gives a closer look to the tools that I mentioned, it will become clear that each of them pays a lot of attention to how this translation is made, which I showed here. It is important part of the design with no obvious way to reuse. But there is another way. While limited and underused, it makes it possible to leverage the translation of separation logic to SMT solver. And only mainstream SMT solver which supports separation logic is CVC5. And to the best of our knowledge, there is no tool that utilizes this feature. And comparing with C3, for example, which does not support separation logic at all. So now I will dive into some more details, and along the way I will tell how to apply the translation. So if you have any questions, you can interrupt me and ask them, or you can save them to the talk. So at first I will start with describing liquid Java and a bit of separation logic and why we wanted them together. Then I will talk about the algorithm to translate frame rule to SMT solver queries, which for the solver which understands separation logic. And then I will talk about limitations of this approach and testing benchmarks we perform. So, liquid Java. Oh, no. Are there any questions so far? Liquid types for Java allow to add predicates to restrict values on built-in Java types. So, for example, here the requirement allows only the doubles which are greater than 0. And the main goal of this tool is to leverage some errors, which are usually runtime errors, to compile time. Like here, we can check that the value we are providing for square root is indeed greater than 0. There are implementations not only for Java, but also for Haskell, C, and some other languages. Haskell's one to be the most mature one. Then I need to talk about separation logic. Not all of it, but rather about things that are relevant to this talk. So separation logic is an extension of our logic, and it brings the means of reasoning about key, and then tries to solve the biggest problem of our logic with the lack of modularity. First, we have ownership predicate that describes the singleton heap. Here it's a pointer P pointing to some memory cell that in this example contains a function. And there is a way to join these descriptions, heap descriptions together via separating conjunction. And the idea is that it is possible to separate the memory, the heap, in two parts, which are disjoint, for which A holds and B holds respectively. And then there is a frame rule which allows to reason about code independently of the context. So we can reason about, for example, about some function and then reuse it in a larger context, relating our knowledge to the context on the call set. We are adding separation logic to the Java because before this extension, the Java allowed only reasoning about reference types or about primitive types because of addressing problem. Then we discovered that it is possible to, with the fragment of separation logic we implemented, it is possible to express simple resource allocation consumption mainly files. Then it is possible to make API for pointer-based data structures like linked list and binary search trees, and then to detect the usage of variables, for example, span streams and iterators. We couldn't implement the whole separation logic because the whole separation logic is undecidable. So we restricted it to a small fragment by saying that it is only permitted to have our logical context. As we implemented our separation logic part for Java symbolic execution, it has had state. So this logical state of our symbolic execution procedure can be in the form of Boolean context conjoined with a simple heap description. So no nested pure Boolean statements inside, only points to predicates and separating conjunction. Then the Java itself provided simplification. As there is no dereferencing operator, we can replace all values with 5 constants, which represent the initialized memory. And the final restriction is that 5 supports grass fragment of separation logic, which, for example, disallows quantifiers inside predicates, which restricts the usage of recursive predicate. Basically, you can't have them like from the box. Let me show the simple example of how this symbolic procedure is reasoning about code. But first, we need to familiarize you with the heap precondition and post-condition syntax. So here you can see function foo, which expects some argument x, and the precondition means that it should be x, which is just initialized. Then the post condition is that this function spits some other variable which is also initialized, but as x is locked in the output, x is consumed. Then there is new. New is not a function, but can be treated as one, and it does not expect anything, so empty heap as a requirement, and then it spits out some initialized memory, which is written in post condition. As pure Boolean part and the heap description are disjoint in this fragment of separation logic, we can read the annotations also, so one can add here the pure Boolean annotation and will work just fine. So as a symbolic execution, one starts with the empty heap and then applies frame rule to add new pointers to the heap. And then the second new, it also applies frame rule and adds the second pointer to the heap. And then, interesting part, one needs to consume A, but as pure Boolean context, here it is covered for brevity, but it actually can be that it's not A here, but some other pointer which is equal to A. So one needs to determine which pointers are from precondition and which one are from the rest of the heap. And this is the core of SMT-backed Frame Rule application. Some magic happens here, which I will describe later, and then the old pointers are consumed, the pointers in the rest of the heap are untouched, and the new pointers are appended to the heap description. So how we should go with the implementation of this heap disjointment to the post precondition and the rest of the heap. So at first we need to check if the precondition is consumable from the heap which is described by the state of symbolic execution. And then we need to split our heap to two parts, to the precondition and to frame the rest of the heap, and then to replace the precondition with the postcondition. And the key part which will help us to implement this is that to make the heap description that contains at least A, we can append start root to it. So for example, if you want to say that our heap contains pointer x pointing to some initialized member and something else, we're just writing this. So it's a good place to ask questions if you have any.
Yes, but not yet.
Okay, there was a yes, but not yet. So, so carry on, Eric.
I can hear you asking
So I don't know if you can hear me, but someone said, yes, I have a question, but not yet. So carry on. There is a question, there is a question.
How do we
Okay, I hear you very, very faintly, but I don't hear you.
I have a short question if you want a question. How do we know
Yeah.
that we need to check pre? So how do we know a priori that it's pre that we want to check and not something else in the whole pre times frame that we have?
So we're arriving, if I understood your question correctly, we're arriving with some heap. And we need to check if it's possible to consume
Okay,
the
so-
precondition.
So the precondition is given to us from the function call, right?
Yes.
Okay, you don't have to guess how to split the heap.
Yes, but we can check if, we can't, if we don't know which pointers, we know which pointers are equal to which from the Boolean context, but we need to, we need to match pointers from the precondition, which we know, to the pointers in the heap description, which with which we came here. Does it make sense?
He's nodding. Nodding.
We've given up on the other mic.
Okay, I didn't hear the last part, so I will carry on. Okay, so the check of the precondition is relatively simple. We are sending to an SMT solver negation, because SMT solver checks for specifiability. The query that we want to check if it holds for every variable which is there. So we are joining the Boolean context with the heap obtain the full context, and then we are checking if our full context implies the precondition and maybe something else. And if one plays a closed loop here, it is also can be treated as, is it possible to consume precondition, which you know from the notations, from the context we came here with. So it is it makes sense to call it the consumable predicate. Then we need to apply postcondition. We're starting with the empty rest of the heap. We're iterating through each pointer and checking if the pointer which we're iterating with and precondition are consumable from the heap. override it. And the idea is that it is only consumable if it's not duplicated here. And if it's consumable, we are adding to the rest of the heap. And if it's not consumable, it means that it's already contained in precondition. Then we're appending the post condition to the frame, and the post condition replacement is completed. So this algorithm brings the overhaul of linear amount of SMT queries with respect to the symbolic description size, and the later benchmark the Java to see if it is forbids the interactive value. So the limitations of this approach, the main two are that we tested only for sequential program and symbolic execution setup, and the most game-breaking ones is that it is very hard to obtain, for example, fractional permissions with this approach, because one needs to modify the logic that is understood by CVC5. The other limitations are that we chose to test this solution with very small subset of separation logic, because we just wanted to see if it's possible. And then it also assumes that it is possible to iterate over description over the pointers in the heap description. So we performed some testing benchmarks. We measured the compile time increase because the liquid Java is plugin for Java compiler, and increased 30% does not forbid the interactive value liquid Java is made for. Then we, as there is no formal proof of the algorithm above, we just tested it with a bunch of annotated parts of the Java, and we applied this algorithm in 3 instances, with function invocations, as I talked about, then the assignments, because if one assigns one pointer to another, it might be possible that the heap descriptions no longer hold, and one needs to go through in the same manner as for function invocations to reassemble the heap that is still hold for the after the assignment. And then branching, ifs are splitting programs into parts, and then one needs to merge the heap descriptions in the end of each. And this also can be done by the algorithm Kirill. We ran through the conclusion, and the main benefit of this approach is that it completely bypasses the right translation to separation logic. The first order logic by hand, it is bound neither to Java nor to liquid types, and it is relatively easy to implement comparing with the manual implementation of this translation. Then there is parse of A. This approach supports only a small subset of separation logic. It is also hard constrained by logic understood by CVC5, and to extend it, one needs to extend the CVC5 itself. So our implementation is available here. If one wants to check out the best place to start test. And I'm happy to hear your questions.
Okay, let's thank Kirill. And I believe there are questions. We'll pass the mic around.
Hi, thanks for the talk. So you mentioned that you were looking only at sequential programs, but I'm curious if so separation logic is being extended by Hearn to concurrent separation logic so that you can reason about concurrent programs and maybe verify concurrent programs. Have you looked into concurrent separation logic support?
As you can see here, it was only tested for sequential programs. It was just not enough time to see if it's possible to support parallel programs. But I believe in the symbolic execution setup it is possible. it is just not explored for liquid channel because time. We just
another question. You said that the limitation is that if you want to add more, you need to extend CVC5. Have you looked at how hard this actually is? Because maybe it's not so hard.
Like the main problem with extending CVC5 in the point of separation logic is that it is very underused. So while we were working on this project, we found a bug in separation logic in CVC5, and it was fixed almost immediately because it was relatively simple and very apparent bug. Just nobody uses this part of CVC5, and to extend it, one needs to write C code. I tried to look into the code of CVC5, and it's doesn't look like it.
Okay, any final questions? Doesn't look like it, and we're about out of time anyway. So thank you very much for your talk, and yeah.